We generalized our concepts and tools for quantum field theory to the case of spin-off fields, describing spin 1/2 objects, spin 1/2 fields. The dynamics of this field when they are free is encoded by the Dirac Lagrangian. This Lagrangian is first order in the covariant derivative. Del slash here uses the Feynman notation, where S slash, for instance, is equal to gamma mu times A mu. And we found an interesting property is that if we squared S slash, we get simply A squared. We took the classical limit and we got the Dirac equation. And in order for the field psi to be also a solution of the Klein-Gordon equation, that imposes a relationship between the gammas, which have to be matrices, and their commutator should be proportional to the metric. That enforces them to be 4x4 matrices at least. So we have for gamma naught squared equal to the identity, and gamma I squared, where I is equal to 1, 2, or 3, is equal to minus the identity, and the anti-commute when mu and nu are not the same. In the Dirac representation, gamma naught is diagonal and it's Hermitian, while gamma I can be expressed as function of the Pauli matrices, and in this case they are not Hermitian. If I want to get the Hermitian conjugate of a gamma matrix, I can easily show this relation that it's gamma mu dagger is equal to gamma naught, gamma mu, gamma naught. By going into the rest frame of reference for a massive fermion, where k mu is just equal to the mass for the time-like component and 0 for the momentum, we found that psi has only 2 degrees of freedom. And when we are in the Dirac representation, these two non-zero components for spinor at rest will be psi 1, psi 2 on the top part of the spinor. So we have 2 independent degrees of freedom, which is compatible with spin 1/2. Indeed, we have 2 projections of the spin along an axis, plus 1/2 or minus 1/2 for spin up and spin down. By requiring the action to be real, we found that the psi bar must be psi dagger gamma naught. Then, by using analogies for Gaussian path integrals for complex scalar fields, we build up a free field theory for spinor fields, and we found the free propagator in momentum space. And the analogy works despite the fact that the spinor field is a much more complicated object. In particular, the psi of x are Grassmann numbers. That means that they anti-commute, so psi x, psi of y is equal to minus psi of y, psi of x. And if I take x equal to y, I have psi x squared equal to 0. We will see when we will use canonical quantization, so when the psi becomes operator, that this will encode the Pauli principle. So we can't put two disturbances of the field at the same position in space-time. That's forbidden by Pauli. But of course we didn't encounter this when we were talking of scalar fields and vector fields, because in that case the spin was an integer and it was a boson. So that's part of the spin statistic connection, that spin 1/2 or half integer spins in general behave as fermions, so we can't put 2 of them in the same state, while bosons there is no such restriction.